This video is about wavelength, frequency, and energy problems. And this first one says convert 790 nanometers into meters. This is something that you'll be doing a lot in these wavelength and frequency problems. So something we need to know is how many nanometers are in a meter. Well, 1 meter has 10 to the 9th nanometers in it. A way to remember that is 9 and nanometer both start with N, 10 to the 9th nanometers. 9 and nanometers. Good way to remember it. Okay, so we're going to take our given 790 nanometers. Going to set up a conversion, drag down our unit, nanometers, and then go to meters. 1 meter has 10 to the 9th nanometers. We're going to multiply across the top, divide by the bottom. 790 times 1, divide by 10 to the 9th. And that's going to give you 7.9 times 10 to the negative 7 meters. The way you're going to type that in is you're going to do 7.9 e negative 7, and that's how to type it in and show it's times 10 to the negative 7. Next problem, we're looking at blue light, and it has a wavelength of 486 nanometers. What is the frequency of that light? Well, we know some stuff about this light. First of all, we know its wavelength. So wavelength, the symbol is lambda, and it's equal to 486 nanometers. We're looking to frequency. There's something else that we know. Now, this is light, and light has a constant speed. And that's going to show up in this equation, c equals wavelength times frequency. So speed of light equals its wavelength times the frequency. Well, c is equal, I sometimes use 3 in class, but on the AP reference table, just a heads up, they're going to give you 2.998 meters, times 10 to the 8th meters per second. So again, I often use 3 in class, but on the AP reference table, they give you 2.998 times 10 to the 8th meters per second. Now notice that we have nanometers and meters. Those are 2 different distance units. So we're going to need to get those to be the same distance unit. So I'm going to take 486 nanometers. I'm going to convert it to meters. Drag down nanometers. 1 meter has 10 to the 9th nanometers. So I'll get 4.86 times 10 to the negative 7 meters. That's what I'm going to use in my equation. Okay, so I'm going to plug these guys in. So for C, I plug in 2.998 times 10 to the 8th. That's going to be equal to wavelength, 4.86 times 10 to the negative 7 times frequency. I'm going to divide both sides by 4.86 times 10 to the negative 7. Now, when you punch this in your calculator, watch your order of operations. If you're typing it in 2.998 times 10 raised to the 8, you'll want to put that whole thing in parentheses just so that your calculator doesn't combine things you didn't mean to combine. And you'll get your answer as 6.17 times 10 to the 14 inverse second. And the way you type that in the answer box is 6.17 E 14. Okay, so one more problem. This one has to do with energy. A photon has a frequency of 5.5 times 10 to the 14th inverse second. What is the photon's energy? Well, frequency is equal to 5.5 times 10 to the 14th inverse second. We're looking for energy. And this time we're going to use a different equation and a different constant. So the equation we'll use is E equals Planck's constant times frequency. Planck's constant is a constant. It's on the AP reference table, and it's H. And H is equal to 6.626 times 10 to the negative 34 joules second. And now all we have to do is plug it in. E equals 6.626. And don't forget that 6 right there. That's what a lot of people accidentally leave out. 6.626 times 10 to the negative 34 times 5.5 times 10 to the 14th. When you punch that in your calculator, you'll get the value for energy. And you'll see that energy is equal to 3.64 times 10 to the negative 19th joules. The way you type that in, 3.64 E negative 19.